මුදමහරියේදී හිර වෙන්නේ නැති වෙන්න SLT Mobitel fiber connection එකක් ගන්න. Netflix බලන්න. ලංකාවේ bestම internet connection එක SLT Mobitel fiber connection. තනතිල්ල දෙසින් සිසිල් සුළං රැල්ලක් හමා යනවා. දිව එනවා පන්දු යවන්න. පහරක් කෙල්ල කරනවා. ඩීප් මිඩ් විකට් කලාපය ඔස්සේ කිසිම සමාවක් නැමොත් ලකුණු 4යි. ටෙස්ට් තරග ඉතිහාසයේ ඉදිමකදී ලබාගත් වැඩිම ලකුණු ප්‍රමාණය ලබා ගැනීමට පිටිකරුට අවශ්‍ය වන්නේ තවත් ලකුණු 34ක් පමණයි.
ලැග් වෙවි ප්ලේ කරන එකට වැඩිය හොඳයි ඉනිම ඩික්ලෙයාර් කරලා දාන්න.
ලැග් වෙවි ගේම් ප්ලේ කරලා ඇති වෙලා නම් ගේමින් වලට ලංකාවේ bestම ඉන්ටර්නෙට් කනෙක්ෂන් එක SLT Mobitel fiber connection එකක් ගන්න.
Good evening, everyone, and a very warm welcome. On behalf of the RoboGames Organizing Committee, I'm pleased to welcome all undergraduate students, academic staff, and mentors to the RoboGames 2025-26 University Category Workshop session. This workshop is designed to give you a clear understanding of the university category, including expectations, technical depth, and how RoboGames aligns with real world engineering and innovation challenges. Thank you for joining us today. We hope this session will be informative and valuable for your RoboGames journey. To lead today's workshop, we have a speaker with strong technical expertise and hands on experience with RoboGames. The session will focus on the university category framework, technical standards, evaluation criteria, and best practices for participation. It is my pleasure to invite Mr. Ignatius Pires, Research and Development Engineer in Scouts. He is currently pursuing his MSc in CSE at University of Moratuwa and obtained his BSc in Mechatronics in Monash University. Please join me in welcoming our speaker. Over to you, sir.
Hello, everyone. Am I audible? Is that a yes? I hope I am audible. Yeah. Can anyone indicate whether they can hear me? Okay, I'm gonna assume so. And yeah, so basically, let me begin. I'll start by sharing my screen. And yeah, so to start the presentation, yeah, everybody, welcome to this workshop. This is the workshop 1 for the university category. So today we are going to be talking about how we go about simulating drones in Webots. So as this is my introduction, basically I was introduced to you all earlier, but yeah, this is who I am. And yeah, so today's agenda will involve these items. We will have a brief introduction to the simulation stack. We will then see how we can set up the simulation environment, then figure out how to communicate with ArduPilot, then see how we can receive camera data, and that all of that will be then that will bring us to our conclusion where we will have a Q&A session. Yes. So basically, jumping right in, the simulation stack involves these things, these items. So Webots, as I'm sure pretty much everyone of you is aware of it by now, because you all have already got access to the GitHub repo. But fundamentally, these are the components. The simulation environment is Webots, and it's responsible for the physics and the sensor inputs. And then we have ArduPilot software in the loop. That's what's known as SITL. And that is what that's basically the exact same code that is running on the flight controller, also running on our computer instead of on the flight controller that it's running, supposed to be executed in. So what it does is it takes in sensor inputs and sends mode outputs and other things like that. So then we have this thing called ArduPilot vehicle controller.py, which is a file that is included already in the GitHub repo, and also sorry, it's already included in ArduPilot SITL, but that allows Webots to communicate with ArduPilot. And then the most critical component, which is the part that you will be evaluated against, is the brains, which is your script. That script will involve taking sensor data from Webots to perform a task. So this is basically a very high level overview of how everything works together. Now you can see that Webots is communicating with ArduPilot vehicle controller, which communicates with ArduPilot software in the loop, which communicates with your script over here. And these are the communication protocols, and these are the communication like types of the data, and the communication protocol that they use. And also I have noted down some common port numbers like IP addresses that you can assign to these. So this is what we are. That's what's typically available, and also what we will set for our example today, and we will see that during the demonstration. And there's also something that I have not yet talked about in this, and it's called map proxy. And I think map proxy is better explained. I can explain map proxy better by showing it you all what it does rather than talking about what it is. So I will do that in the demo. So that brings us to setting up our simulation environment. So when we started like this task, we received a fair bit of complaints. Like personally, I faced some problems as well because the Docker containers was a bit slow to start, and therefore I decided that okay, maybe other people are also having the same issue, which is why I included this section. So I strongly recommend using a Linux distribution instead of Windows, because nobody who programs real robots uses Windows. I'm sorry, but we typically use a Linux distribution, so that because all the software that we use is built for a Linux distribution. So the following presentation also assumes that you're either are using Ubuntu or will be using Ubuntu 24.4.3 LTS for your projects. So setting up the simulation environment simply involves these sections. Like I told you earlier, you have to install an ArduPilot. So you have to install ArduPilot basically, and then you have to set up ArduPilot software in the loop for Linux. Now, by going, all of these instructions are there in the documentation. And actually, if you take a quick screenshot of this, the links, they will show you exactly how to install and exactly how to configure. This should take you about 2 hours, and if depending on your internet connection, of course. And following this, you should have a decently set up a simulation environment, and that is what I will demo now in a short demo environment. So I'm going to stop sharing my video and instead share my, So this is my, I've opened a terminal, and basically what I've done is in 3 different terminal panes, I have opened up the different things. So firstly, I will need to, this is basically how you communicate, switch on or basically activate ArduPilot software in the loop. So there's this you by by following a similar command structure to this, you can basically run this thing called simvehicle.py, which is actually what we are running in the Docker container as well. So simvehicle.py, you give it the version vehicle calling ArduCopter, and we say that this is for Webots Python, and I'm giving it a parameter file, which is something that ArduPilot still understands as the parameters that the flight controller contains. And this thing is already given a link, like I have given it a particular folder, and that folder is the one that's there in the same in the repository for the for RoboGames. And yeah, notice that I have said this out equals UDP colon 127, basically localhost 14550. Notice how it is exactly what I've shown that y'all here. It's exactly the same as, give me 1 second. It's exactly this. So this was enabled by running this command. Okay. So I'm going to switch on ArduPilot Citadel, and it's going to open up a bunch of windows, but that's all normal. Yeah. Right. So the map is not exactly necessary for now. So I'm going to close it. But it says link 1 down. Why? Well, we will see soon enough. So now we have ArduPilot software in the loop running. We need to open up Webots. So I changed my directory to the IESL RoboGames University Phase 1 repo. And in there is a world file called iris modified.webot. I open that by running Webots, this thing like that. And it is very helpful if you all have, yeah. So that will load the world, right? So now we can see that we have the Iris quadcopter. However, if we look down, we say info, Iris, external controller is waiting for local or remote connection. That means those two are still not communicating with each other. Remember that I discussed here that ArduPilot vehicle controller needs to be there for Webots to communicate with ArduPilot. And that is exactly what we should run next. So we are going to run. So basically, I use this software called UV. You can replace that command by, so it's the same, it's in effect the same as saying Python 3, Python 3 Webots controller .py. So it's just something that's exactly like Python, just like it just allows me to run Python scripts as well. But basically what I'm running is I run the ArduPilot vehicle controller and I specify motors and I specify a camera called camera and a camera port at port 5599. I also give FPS as 20, which, and that is what this is. You can see that the Webots camera that you are listening to was set up in this part. So it's going to give some a large amount of errors like this. But look at what happened. Did you see the rotor spinning? The rotor started spinning, which means that, and I'm sorry, it's not very clear, but it says Iris external controller connected. And notice that this thing, which was earlier dark, is now the color gray, which is the same color as this. Basically, this is the camera stream, and it's now streaming the camera. So that is what it'll look like when you have the simulation environment set up. You can also like exit this and just restart it, and it'll show you because I restarted because there was like all of these warnings that were happening that I don't really want to see it printed out. But look, it says camera stream started at this, which is what we said earlier, and it's listening to ArduPilot software in the loop, and it's also connected to ArduPilot software in the loop. In other words, we have done this, we have done this, and these two are already communicating with each other. So this is working fine, this is working fine. What's missing is this. We have to get to that. And that is what we have to talk about in the upcoming slides. So basically, yeah. Give me 1 second. Yeah. So basically, when we communicate with ArduPilot, we use this protocol called Mavlink. So Mavlink is a very lightweight protocol for communicating with drones, which is what they have described it as. And as you can see, if you all are familiar with communication protocols, have any experience at all with communication, you all can see that it's a very like a very standard sized protocol, but it's a very by judging the number of bytes within the protocol, you can say that it's actually very compact. It doesn't use much bandwidth basically, and it also has features that like improve the reliability and the security aspect, reliability and security aspects of this message. But so basically, Mavlink is what we use to communicate with ArduPilot, and it's a messaging protocol. And we can send Mavlink packets over TCP, UART, ExpressLRS, CAN bus, like, and others. Like, if any of you have already have played around with drones, you all might have an idea of what ExpressLRS is. It's basically a radio communication protocol. Like, you use it for remote controllers for drones. So Mavlink is so flexible and versatile that you can use it in even that scenario. It's a very cool protocol. Yeah. So communicating with ArduPilot we will be like, when we are communicating with ArduPilot, for now we will consider just TCP/IP, as we are focused on simulation. Of course, later down the line, when you're actually going to deploy the software, like when you're going to actually deploy your code onto a drone, you might use other interfaces, but for now, you will use TCP. And assuming Python as the programming language that you're going to be using, there are three main libraries that we can use to send Mavlink data. So there's PyMavLink, which is very low level and supports every PyMavLink dialect, which means that so it's able, it's usable in most flight controllers which communicate in Mavlink. So not most, all, because it supports all of the different variations and quirks of these different flight controller softwares. So PX4 is a flight control software, ArduPilot is a flight control software, things like that. Then there was DroneKit, which was a very high level, very popular library that abstracted away all the low level nitty gritties of communicate like direct PyMavLink communication. But it is unfortunately no longer actively maintained, and I do not recommend trying flying around with software that is potentially outdated. Like it is also, yeah, I do not think it is been maintained in several years. Like there's not received updates in several years, so we will not exactly focus on that. Then there's also Map SDK Python. This is also an option. It is high. It is high level, and it makes it easier for us to work with ArduPilot, PX4, and other flight controllers that communicate with in Mavlink. However, support for anything other than PX4 is uh, is not great, because the idea behind Mav SDK was for it to be used primarily for PX4, which is the flight controller software that people have that's from the same people who created the Mavlink. So basically, there's this foundation called the Drone Code Foundation who support these projects. Called so they are responsible for creating Mavlink, creating and maintaining Mavlink, Mav SDK, PyMavlink. So this is an optional. This is a SDK that we can use if you want to do something high level, but it is, as I mentioned here, it's not very great in with ArduPilot. So now let's get to the meat of our discussion. So these, yeah. So this first script is basically, so let's just jump right into code. I'm pretty sure you all are a bit eager to get started. However, so directly using Mavlink, what does it look like? So there are many resources available online, especially from like I believe our GitHub repo also has some very useful links. However, the connection flow basically goes like this. We need to connect to the flight controller using this UDP address that we set earlier. And it listens to this thing called heartbeat message, which all flight controllers have to send, flight controllers and ground control stations have to send, just to show that they're online. So we will listen to this heartbeat message and then continue our script. And basically, this is just some uh, additional feature, it's an additional functionality that tells us whether we are what type of flight controller we are connected to, and what type of vehicle it is. It could be a plane, it could be a drone, could be a rover, different things like that. And then there's this bit of code is just don't need to be very concerned about it, but what it basically does is it's there to tell the flight controller to send us this particular message type at a certain rate. It's telling, okay, so you can think about it like it has a database. We are telling this flight controller to publish all of these messages. Just keep publishing them at a particular interval, and I need this message for some functionality later. But basically, we we get the altitude that we started, and then we move to this thing called guided mode, which basically means we are sending commands to the flight controller, and it is a flight controller from something that's via Mavlink. Via Mavlink from a companion computer or some other device that is capable of communicating like using Mavlink or rather than a remote controller or something like that. So there are different modes for ArduPilot, like different flight modes. Either it can stay in one position, it can go to a GPS location, it can execute autonomous, it can execute a mission that has waypoints, can do multiple features like that. And in that, we have this mode called guided, which basically means go to these points, and these points that I'm giving you, I have given them to you via a script. That's what that guided mode acts like. And you can find out more information like in either GitHub issues or yeah. This rather gnarly looking block of code is something that you commonly see in PyMavlink. Either you can I believe you can make it better, but this is actually what we are sending. We are sending a command to a target system, to a target component, telling it to take off and go to flight altitude. What are all these zeros? These are actually parameters that we are not like. If you look into what the parameter, like what a Mavlink packet, like a particular packet, and what its parameters are, you can see. So this is parameter 0, 1, 2, 3, and it goes on, and all of those are not included, but all of those are not relevant to this thing. So that's why I've set them as 0. But so yeah, so and yeah, that allows us to take off autonomously. And while this bit of code, what it does is it's just checking whether the flight altitude is like 95% of what we expect it to be. And then after we reach that flight altitude, we are going to return back to launch. And this basically, yeah, that is the meat of this code. Now let me run it and let's see what happens. So I'm going to run it via this command, and it shows that, okay, we are taking off. And yeah, shows the altitude is 2.03, target altitude reached, returning to launch, and also scripts. The script shows all the altitude as it changes and reduces. Yeah. So that's the first 20 points, I think. Yeah. So yeah, now that we saw what PyMavlink looked like, let's see how excuse me, what Mav SDK would look like. So when using Mav SDK, it is a bit more high level. So we still have to connect to the drone, obviously. However, we have far fewer, like as you can see, we don't directly send Mavlink messages. We call functions which underneath are responsible of sending Mavlink messages. So this is why it's a very high level library, and that is why it's also very much more ergonomic and easier to program when you are using PX4. But there are some caveats when you're using ArduPilot. However, let's just try running this and see what happens. So ideally, what should happen is it should run exactly like the earlier script. Now we see the drone is taking off. Pay attention to what happens in this section. I kind of forgot to explain what this section, what this interface is, but this is what is known as Mav proxy. So Mav proxy is actually it's like a command line that you can use. It's called a ground station, ground control station software, which basically means it allows you to send data to and receive data from a flight controller over UDP or UART, whatever. It has a bunch of features that we are not using, such as routing Mavlink messages from UART to an Ethernet endpoint, UART to an TCP endpoint. It can do a variety of different things, but for now, we're just using it as a ground controller. What is a ground controller? Well, so in case that wasn't very, I'm pretty sure that explanation needs some improvements. So let me just show you what map proxy can do. So when we ran this command earlier to start ArduPilot CITL, we actually also started map proxy, which you can see here. So this is the map proxy command line, and what it allows us to do is to be able to manually send commands to this send commands to ArduPilot, so that we can play around with the drone without having to write any scripts, without having to worry about Python or anything. So how you do that is, so you wait until you have connected, and after you are connected, you have to wait until this section called pre has turned from red to green. That is saying that the pre-arm checks are passing, which means that it should be good to fly. Pre-arm checks basically involve checking whether there's RC, checking whether there's battery level, checking whether there is GPS location, checking whether the internal location estimate is good also, because you are basically, it's not just GPS, right? It uses its other sensors as well to get a more precise estimate of where it is. So all of this is being done in the background. But when this pre-message goes from red to green, that means that we are ready to take off. So we are currently in the land mode. Let's transition from the land mode to the guided mode again. As you can see, nothing happens. Nothing happens yet. So to arm the copter, we type arm throttle, throttle, didn't type it correctly. And then to take off, we type takeoff 3, which takes off and flies to an altitude of 3 meters, which you can see right here. So after 3 meters, it's just going to stay there. Now, once we are here in guided mode, you can move your drone forward, guided, by typing guided forward, let's say 3. And now we can see that the drone is moving. And we can make it return to its launch position by setting the mode as RTL. So set mode RTL. And now the drone will return to where it was launched from. So that is basically what map proxy can do. It is not just a command line. It's basically a full-on interface for you to send Mavlink commands and listen to what the drone state is from your terminal. It is, if you all have worked with something like Mission Planner or Q Ground Control before, that this is basically providing the same functionality, but in a text form. Yeah. So you can also set different GPS waypoints and go fly to different locations from within map proxy as well. So yeah, with that brief detour done, let's get to the other part. So I have set it to always on top. I'm not going to do that anymore. So yeah. So this script demonstrated how to use basically Mav SDK. Now, I'm pretty sure that most of you all can figure out how to, take off and land, as it's not that very complicated. That's not very complicated. So let's go to something that's a bit more involved, but still we are building on the same foundations. So the meat of the script is basically the key changes that we have from the earlier takeoff and land script is that we are going to be arming the motors, and it's going to fly in a particular pattern. and then it's gonna land. So earlier we just took off, and as soon as it reached its height, it landed, right? Now, what we're gonna do is we're gonna go to a certain altitude, and then we're gonna fly a pattern, and then we're gonna land. So a lot of this code is there to so that we can see what the internal state of the drone is, so that we are not blindly just telling it to do this, do this, do this. No, we want to see what it is, what its state is, because otherwise it's going to send an error message our way and we won't be able to catch it. And we want to be able to catch it so that we can respond to it. So a lot of this code is just error handling, and not error handling in particular, but setting up these message rates, and also making sure that the flight controller has responded to what we have asked it to respond, responded to our command. And yeah, the key difference from the earlier script is, as we can see, we have this little bit of code called fly square path. Now we will send a special type of message called set position toggle local net send, which is also there in the documentation. Do not worry if you don't exactly remember all this. Go to ArduPilot, go to Copter. So go ArduPilot documents, Copter, then go to what commands are available in guided mode in ArduPilot. What commands are available in guided mode, and then you should be able to see all these messages that are available. So yeah, and here I'm just saying, okay, using this frame of motion, with these and only considering these parameters, do something like this: go half meters forward, proceed with a velocity of half meters forward. So forward, and then we wait for like 5 seconds for it to do that, and then we switch to turning 90 degrees, which is achieved by using this map command called map command condition yaw, and we are setting 90 degrees, and this is done in a clockwise, and we are turning it relative to where it was. So you could either have it absolute 90 degrees, as in, I believe it's a compass 90, relative to north. And yeah, so this thing is just saying, okay, turn 90 degrees from wherever you are. And we do that 4 times. Basically, we are drawing a square. So now let's see what happens when we run that command. So we have connected to the flight controller. The drone has begun its ascent. It's taking off. It has reached the target altitude. It's moving forward, turning 90 degrees. 90 degrees again. And yeah, as we can see, square pattern has been completed and it's returning to launch. And shortly it will automatically launch, return to where it took off from, which is the top of its box, top of this box. And it is possible for it to sometimes, fall off the box. Completely normal. Just restart the simulation and the restart the simulation, basically restart everything, and then you should be back to normal. If it falls off, you can also place it from to the top of the box, but it's a bit tricky to do that. So just restart everything. It only takes like 10 seconds. Yeah. So, right. So with that being said, okay, not from top. Yeah. So Right. So that brings us to what you can. So basically, that demonstrated what you can do with Mavlink and guided mode. Basically, you can control the drone in any way that you can imagine using guided mode with Mavlink. You can make it go straight, go increase altitude, decrease altitude, go in a circle, orbit a certain point. Orbit a certain point in the sense it looks at something, and then you can make it look the drone face a certain point, and then fly in a circle around it. You can whatever like flight motion that you want to capture, you can capture it with you can code it using Mavlink, using PyMavlink. Yeah. So there's another component to this task, the task that you have to do, and that is the vision part, right? So we have not yet talked about how we can receive camera data. Now, we are going to be receiving a raw binary stream, which is sent by this ArduPilot vehicle controller, and we can access that using Python. You can go to this link here, and that link is basically what almost verbatim what I use for this for the following demo, like for the first demo at least. It shows you how to receive shows you how to whether so this is basically it's showing us how to receive camera check the plan. Yeah, showing us how to receive the data and display what we are receiving. So remember, we are already transmitting a footage from the camera of this drone. So what we should do is just run this command. Give me 1 second. Okay. It's a gray color box. Fortunately, like which doesn't tell us much, but like it's the same camera feed that is here. Now let's see what happens when we use map proxy to make the drone take off, and let's see whether the feed changes. So let's go to mode. What is the mode? We go to mode guided. Arm throttle. Then we take off to 3 meters again, and let's see what happens. There we go. We have received our camera stream from a Python script. So that's basically what that script does, and that's how you can do the same thing. Using if you just go to this link, they have the almost the exact same code that I used to achieve this. Now let's refine the code that they have given over there to do something more. So now remember, our drone is still flying and it's airborne. Let's go to something a bit more advanced and uh, try to display whether there are any April tags to show the April tag IDs. And if there are yellow lines, basically segment them. Like basically uh, perform some feature extraction on the image to only extract the yellow lines so that we can use it for something later. Now, I was not able to completely find the yellow line, like completely finish the yellow line code, but I think still the illustration for illustrative purposes, it still does the job. This is the second part of the puzzle. Yeah. So once again, we are going to be connecting to camera here. Yeah. So I'm gonna tell so my screen is kind of crowded right now. There are so many interfaces on it. I'm really sorry for that, but yeah, when you're working with drones, you basically need at least 2 screens. Yeah, let's move forward and see what happens. So we do that by guided. Let's say forward. So we'll move forward 3 meters. And yeah, so the Aruko and April tag detection has still not found anything. So let's go forward a bit more. Still not in view. And it's still not in view. And there we go. We are receiving, like, OpenCV is capable of natively detecting Aruko codes and April tags, and we are able to use that in the for our task right here. Now I'm just going to RTL so that we can stop this. So hopefully I can't exactly share a lot of the code that is being used, because this will be part of this is going to give the answers to some of the tasks that you have to do. So unfortunately I won't be able to share a lot of it, but know that so after we figure out how to receive the camera stream, we can use OpenCV and its features to perform April tag detection, perform feature detection to detect the yellow lines. Even though we are getting a grayscale stream, we can basically use these to ArduPilot and OpenCV together to develop an intelligent script that is capable of navigating autonomously. Yeah. So yeah, that honestly brings me to the end of the presentation that I have today. So in this workshop, we discussed the different components that make up a simulation environment and how they communicate with each other. We saw what part Webots plays, and uh, ArduPilot vehicle controller.py and ArduPilot software in the loop, how they work with each other, and how you can communicate with ArduPilot and the Webots through the different interfaces. We also just got a slight taste of how to control a drone via Mavlink using PyMavlink and MavSDK Python. However, I do recommend that you stick to PyMavlink. It is for ArduPilot, it is much more reliable, like much more easier to use, even though it's high level. Even though PyMavlink can be intimidating at first, give it 2 days and you will figure out, and we will be you once that 2 days is done, you'll be more like familiar and ready to and it won't intimidate you, basically, is what I'm trying to say. Just give it a couple of days, struggle with it, and you'll come out just fine. We also learned how to access a camera stream using Python and OpenCV, which is what I demonstrated. And we also had a brief overview of the resources that we use to develop your submission for the completion. Now, yeah, with that being said, that's the end of my talk. If you all have any questions, feel free to ask. If it's related something I can't answer, I will. And yeah.
Sir, there's one question in the Q&A. Is it impossible to do this on an Ubuntu virtual machine?
It is absolutely not impossible. You can do it. It's just that it might be a bit slower, but it's definitely possible on a virtual machine. Yeah, it's easily possible. It's the most simple way to do it, I would say, if you're somebody using Windows. Simple and reliable, yeah. I'm going to stop sharing my screen now. Yeah. Okay, and I see that there's another question saying, mention all the resources you recommend to learn everything from the beginning to complete this project. Basically, the resources I recommend are what I already talked about. If we go to the README of the repository that we have provided, that README contains several links that will take you to the ArduPilot documentation, the Webots documentation. But yeah, so it will help basically read the documentation. That'll help you learn. But there are also some YouTube channels that I use to learn stuff from. I think some of them were called the Drone Dojo or something like that. I don't really remember. But when I was getting started, I think I learned a little bit from those channels. But mostly it was trial and error because we can. It's simulation, right? You're not going to break anything. So just try, work, and try. However, I also have to mention that we could also get an LLM to support for our work, right? So it is somewhat able. It will get you, let's say, 60 to 70% of the way there sometimes. Except some, it does make errors, and when though to debug those errors, it is best if you know what those commands do. And yeah, so honestly, I do recommend reading the documentation. If you don't understand anything, you could ask an LLM, which has access to the internet. But also, you could look at the discussion forums and other things. You can ask your friends. You can work on it together. Those are the resources that I think. Uh, the marking criteria and I think is already provided in the task description, I believe. Isn't that right, Nadisha? And the guys?
Say, so if the each section of the task is completed by in the team simulation, all those points will be awarded. So that's how it's
Right.
for like takeoff success, there is 20 points. For line following accuracy, we give 30 points. And to detect the field tag and print the value, we also provide 20 points. And to finally successfully land in the third base, we will provide 30 points. So if your simulation done all those means is section successfully, these scores will be provided.
Right. Does that answer the question of I hope that answers the question. If not, please expand on what you meant by that statement. Okay. So yeah, we will be getting this document. I could share this with I can share this slideshow with y'all. Unfortunately, I'm not allowed to share any scripts with y'all for this. But yeah, I could share this slideshow that I used, which has links to all the things that I talked about, so that you can just very easily, it's much easier for you to follow and get your environment set up. So yes, you can. Okay, so the next question is, can we use VS Code? You absolutely can. That's what I'm using, and it's just I'm not. So I'm just not showing the. Okay, I'm not sharing my screen, but it is also what I use, so it's fine. You can use anything you want. Get a random issue of the drone suddenly failing pre-arm checks acro bell roll pitch. Good question. Okay, so could you explain when this happens? So suddenly failing pre-arm checks are okay. I think this happened to me also. That was due to I cannot reliably reproduce this issue personally because it has happened to me as well. I believe it is due to, maybe our simulation is running a bit slow. That is a possibility. And so it interferes with the way that the sensor data is being sent. So it could be one possibility. But basically, yeah, hopefully, like, I don't really have a good answer of this. I think there's some debugging that you can do. However, you can also just turn off the pre-arm checks, which is not recommended for a real drone, but you could turn off the pre-arm checks and see if it flies and if it crashes. Yeah. If it crashes, then that's a concern. But yeah. So why does no VNC take a long time to connect with ArduPilot? See, that's very true. That is exactly why I made my development environment. Like, I created my own development environment, right? So I'm not exactly sure why no VNC takes a long time. But we have to understand that every single time when we are running the start.sh, it starts the Docker containers, and each Docker container has to run this compilation step for ArduPilot. Okay, I'm not sharing my screen. I'm going to start sharing my screen. Okay, I cannot share my screen, but it's fine. It's fine. Basically, there's compilation step that happens every single time you run sim vehicle when you start ArduPilot software in the loop, which takes up a large amount of time. So it takes like 2 minutes to do. But fortunately, you don't have to do it again and again. So once you set it up, just leave it as it is, and you should be good to go. So yeah, and repurpose. Okay, for Windows users, what do you recommend? WSL or VM? It's a tough question. I haven't used WSL recently, and I'm not sure how exactly it will perform when you have like GUI interfaces, because you see Webots is a GUI interface and map proxy is a GUI and stuff like that. Not sure how exactly it'll work. I think the most reliable way to go about it is with a VM. However, I understand that you're not going to have access to GPU acceleration on a VM, very likely. But I'm running this on a ThinkPad, so like it's 5 years old, so it doesn't need a lot of performance. So in other words, what I'm trying to say is you can use a VM. I think it'll perform fine. Yeah. WSL might also work and it might be convenient, but VM is what I'll do if I was just getting started, because yeah, I don't want to mess around with the command line for now. If I was just getting started. Ubuntu can be used, yes. Do we need to have exactly 24.04? No, I'm not. See, I think we use Ubuntu 22.04, basically the earlier LTS version for our Docker scripts, which also works. I just use 24.04 because it's on my computer, and also like I know that it is compatible with Webots, the Webots version that I use, and stuff. Yeah, so that's why I use 24.04. Also recommend it. I mean, it's just newer software with newer libraries, and yeah, why not, right? Yeah. So, if you all have any more questions, so I see the Drone Dojo. Yes, it is actually the Drone Dojo on YouTube. So I'm gonna share a sample. Okay, let's see playlists. Okay, I have watched exactly 4 videos from there. But yeah, copy, and if that's okay, I'm gonna link this in chat posts, and yes, I hope this is fine. Yeah. So that's the playlist, and yeah, you can go and watch those videos. Will receive a 10 FPS video stream be sufficient for a smooth line follow? Is it normal for Webots to look laggy? Webots, I mean, the camera looks laggy because we have set it to 10 FPS, right? So you can, okay, I'm not entirely sure whether we are like somebody using the Docker container can change the frame rate of the camera. But when I ran my controller, I set it to 20 FPS. So I did that right here, and I'm not sharing my screen. So when I shared my screen, when I ran my this ArduPilot vehicle controller to Pi, I specified camera FPS as 20. You can increase the frame rate. not entirely sure how a line follower will perform with that, but see, you don't need like fundamentally, I don't think you need a really high frame rate for that problem. But yeah, you can. I don't know how to answer that question. Yeah, it's like maybe it may not be enough, but try. You can try it. Okay. Any more questions?
Thank you, Mr. Ignatius, for that comprehensive and insightful session. And thank you, participants, for this engaging discussion. To formally express our appreciation, I would now like to invite Mr. Praveen Navaratna, the chairperson of the RoboGames Organizing Committee, to deliver the vote of thanks.
Uh, I hope that I'm audible. Yeah. So, hi guys. First of all, to start off my official vote of thanks. So, first of all, I would like to thank Mr. Ignatius Perez, our speaker for today, for fitting this into his busy schedule and guiding our participants through the Webots session. And it was a really great session. I hope that you all enjoyed it as the participants, and also that it helped you get insights and a good experience to complete a task really well. And also, then again, none this session would not have been possible without you, the participants. So thank you for joining this session, and thank you for having trust in us with the sessions, and thank you for having trust, and thank you for joining RoboGames as well. So yes, and also finally, I would like to thank my organizing committee who went really far with organizing this, and they have done a really good job with organizing this. So yes, yeah, with that, I would like to finally invite you all to get do this task really well. And also, if you all need any help with the task or anything other than the task that is related to RoboGames, please feel free to contact us. So we will send you all details of contact persons that you all need to contact. And also, if you all need to contact, if you all have any language barriers or language issues from your end, do not worry. We have support for that as well. So if you're either language is Sinhala or Tamil, we have people who can help you all with the language issue. So yes, feel free to contact us if you have the language issue as well. So we are really happy to help. And also, um, anything technical or non-technical, feel free to contact our organizing committee. They are always open to questions and always open to help you. So yes. And finally, once again, I would like to end my official vote of thanks by thanking you all once again, the organizing committee and the participants and Mr. Ignatius Perez. Thank you.
You're welcome. And yeah, thank you everybody for attending this session. And yeah, thanks for listening. Yeah.
Thank you, everyone. Before we conclude, I'd like to make a couple of important announcements. The deadline for initial task submission has been extended to the 20th of February. Make sure to follow the submission guidelines which have been shared with you. If you have any questions regarding the submission process, feel free to contact the following people: Hasini Lavanya and Yanushka Gnanasegaran. With that, we come to the end of today's University Category Workshop session. Thank you to our speaker, organizers, academic staff, and students for your active participation. We hope this workshop has helped you clearly understand the expectations and the opportunities offered by RoboGames. We look forward to your innovative ideas and strong participations at RoboGames 2025-26. Thank you once again and good night. Signing off, I'm Madhumai Swendar.